We start a new lecture on statistical tests, and we will see different kind of testing different features of the data, and we will start today with the comparison of proportions between two groups. So let's say that we have two groups. One will receive a drug, the other one will receive a placebo, and we want to measure what is the probability that a given event happens in each one of the two groups. So in particular, this drug is apixaban 2.5 milligrams per day, or twice a day, and the event we are interested in is the recurrence of thromboembolism. So there is a clot formed in some vein. So we have these two groups, the one having placebo, the one having treatment. We follow these people for a year, and then we count how often or how many times each one of these people had a recurrence of the thromboembolism. And for the placebo group, we have these numbers. So 73 had a recurrence, 756 didn't have a recurrence, and for the treatment 14 and 826. So we may sum this table. This table is called a contingency table, and a contingency table has two entries. So a row entry, and in the rows we have put here the treatment, and a column entry, and the columns we have put what is the outcome of the result, so recurrence, no recurrence, and then the cells contains the counts. So we may sum by rows, we may sum by columns, we may sum all the numbers. So almost 1,700 people participated in this study, and we can compute the probabilities of having this recurrence. So for instance, for the treatment group, the recurrence is 14 divided by 840. For the placebo, it is 73 divided by 829. So that test, and we will not see the specific mathematics for those are rather complicated, but there is a test that is called the Fisher's exact test that calculate whether the proportion in the two groups is different or not. So the null hypothesis is the proportion of recurrence of those receiving apixaban is the same. There is a mistake here, this should be P. So it is the same as the proportion of people having the recurrence when they receive the placebo. So if the null hypothesis is true, then the drug doesn't have any effect. So the Fisher's exact test computes what is the probability of observing 14 out of 840 people, 14 recurrences, or even more extreme. So even more extreme is either much smaller than this or even much larger than the complement. The complement is 826, so 826 or more, or 14 or less. Actually, that is if we are looking at the two-tail test. If we are looking at the single tail test, then we are looking only at the 14 or less. Okay, so the p-value in that case turns out to be in the order of 10 to the minus 4. So we can reject the null hypothesis and conclude that the treatment is having some effect. Sometimes the Fisher's exact test is computationally difficult to apply, especially for large samples, because you have to enumerate many possibilities, and then making the calculations for all those possibilities is costly. So the Fisher's exact test can be approximated by a chi-squared test. There are some conditions for this approximation to hold. Okay, so but we already know about confidence intervals. Can we reason in terms of confidence intervals? So we have the proportion of people having recurrence in the placebo, so just a reminder of the numbers. So it is 73 divided by 829. This is 8.8%, and the 95% confidence interval is between 7 and almost 11. And for the treatment group, we see that this probability is much smaller, so it is about 4 times smaller, or 5 times smaller, and the confidence interval is this much. Okay, so the difference between these two numbers is called the attributable risk, and the ratio between the two numbers is called the relative risk. So the relative risk, that is the ratio between the two, is almost 0.2, so that is 1/5. So that means that having a recurrence, if you are receiving the treatment, is 5 times less common than if you are receiving the placebo. And we can also put the confidence interval on this relative risk. So the confidence interval in this case goes from 0.11 to 0.33. So that is, it can be, we have observed 5, so it is 5 times less common, but it could be somewhere between 9 times less common or 3 times less common. So from our study, we may learn some other features, but these other features are secondary results. For instance, the reduction is similar by age and sex, or patients receiving the treatment did not have more bleeding than those with the placebo. And so these secondary results, as we have learned already in the previous lectures, if they are of sufficient interest, then we can now make a study in which this is the primary outcome we are looking at, and then we design our study just to so design is basically deciding the sample size and how to organize the patients in groups, so that we can faithfully analyze this result. So there are some assumptions when we do a test, and as always, these are the main 3 assumptions. Normally these are the assumptions of most tests, that the sample is random, the observations are independent, and there is no difference between the two groups except the treatment. So let's see each one of them. So we want a random sample, so that is that the sample is representative of the whole population, and the subjects may not be randomly selected. So for instance, they may come from hospital, but they are randomly assigned to receive the drug or placebo. So this randomization makes this random sample to be more fair and to be more generalized. And as always, if these are people coming to hospital because they have a particular disease, in this case it was thromboembolism, so this result only extrapolates to the population where this sample is representative. So it is only applicable to people that have already had a thromboembolism. It doesn't apply to the whole population. Then observations are independent. So selecting one member of the population should not change the chance of selecting anyone else, and the results of one person is not correlated to the result of any other person in the study. For instance, if we include several members of the same family in the study, this assumption of lack of correlation is violated. And can be really the case in those diseases in which there are not so many patients, and then there is a genetic trait of genetic basis of the disease, and then we include several people from the same family because those are all we have. But then we are biasing by our sample by these genetic traits of these people that of this family that is overrepresented with respect to the whole population. And the assumption that there is no difference between two groups, so we have to show that there is no significant difference in terms of age, weight, sex, kidney function, just to make sure that this difference is not due to some random fluctuation of any of these variables. So for instance, let's say that the people, just by chance, the people going to treatment, they had less weight than the people going to placebo. So it might be the difference in weight and the difference in fat that made this result. And just to avoid that, so beside analyzing our variable, the drug or placebo, we have to analyze any other variable that might influence our data. So this is all for today, and see you tomorrow.